Right now, the Virtual Telescope project in Italy is observing an interstellar comet whose ion tail has expanded to zero point 0.7 degrees on the sky, wider than the full moon, in just days, which contradicts every known model of cometary outgassing for objects this far from the Sun, leaving scientists unsettled. The comet is 3I Atlas, only the second visitor from another star system humanity has ever tracked, and the speed at which its tail is lengthening defies expectations. Objects traveling in from the outer solar system usually brighten gradually as solar heating builds over weeks or months. This one erupted. The photograph from November 10th, assembled from 18 long exposures taken through poor observing conditions and a bright moon, shows a sharply defined, intensely luminous tail that dominates the frame. Something inside this wanderer is boiling away at a furious rate, and the violence of the transformation is happening faster than theory predicted. Here's where it gets interesting. The tail is not merely long, it is structured. Fine striations run through the electric blue plume, signs of magnetic turbulence or episodic outbursts. A faint anti-tail has also emerged, a ghostly projection caused when sunlight scatters off dust particles aligned along the comet's orbital plane. Anti-tails are rare and short-lived, visible only when geometry and dust density align perfectly. Their appearance here suggests that 3I Atlas is shedding material in complex waves, not a steady stream. The comet is not simply melting, it is rupturing. Preliminary spectroscopic measurements reveal an abundance of carbon dioxide ice far higher than expected. CO2 is volatile, but it requires specific formation conditions, extremely low temperatures, far from any young star's heat. Most comets in our solar system formed in regions warm enough that CO2 either never condensed or was quickly lost. The fact that 3I Atlas retained so much suggests it was born in a colder, more distant disk than the one that built Jupiter and Saturn. Possibly it came from a system where giant planets never migrated inward, leaving the outer reaches undisturbed for billions of years. Possibly it formed around a dim red dwarf, where even the habitable zone lies closer to the star than Mercury orbits our Sun, and the comet-forming region extended into near absolute zero cold. The chemistry is a fingerprint, and the fingerprint does not match anything in our stellar neighborhoods catalog. Stop and consider that. If the CO2 abundance is confirmed, 3I Atlas is not just a comet. It is a surviving fragment of planetary formation from a system whose architecture may be radically different from ours. Every molecule now streaming into space spent billions of years locked in ice, shielded from cosmic rays, untouched by our Sun's warmth. When ultraviolet light from the Sun strikes that ice, it strips electrons from the gas, ionizing carbon dioxide into glowing plasma. The solar wind, a supersonic stream of charged particles flowing outward from the Sun at hundreds of kilometers per second, catches those ions and drags them into a tail. That tail is not debris. It is ancient chemistry, unsealed. Here's the problem. The rate of gas production implied by the tail's brightness and length does not align with how much sunlight 3I Atlas is receiving. It is still beyond the orbit of Mars, where solar heating is weak. Most comets this far out show minimal activity, faint comas barely detectable even with large telescopes. Yet 3I Atlas is blazing. Either its surface is extraordinarily dark, absorbing nearly all incoming light with ruthless efficiency, or subsurface layers are superheated, conducting warmth inward faster than expected. Or something else is driving the outburst, crystallization of amorphous ice, which releases stored energy as the ice changes structure. Radioactive decay if the comet is unusually rich in long-lived isotopes. Exothermic chemical reactions triggered when frozen compounds mix for the first time in eons. Each explanation is plausible. None is proven. The data do not yet distinguish between them. Scientists are reacting with a mixture of excitement and caution. Dr. Elisabetta Dotto, an expert in small body dynamics at the INAF Astronomical Observatory of Rome, noted in a preliminary release that the rapidity of the tail's growth is unusual but not impossible. Comets are notoriously unpredictable, she said, particularly when their composition diverges from solar system norms. Dr. Matthew Knight, a planetary astronomer at the U.S. Naval Academy, who has studied both known interstellar objects, Oumuamua and Tui-Borisov, pointed out that interstellar comets may retain more volatile ices simply because they spent most of their existence in the deep freeze of interstellar space, where temperatures hover a few degrees above absolute zero. That preservation could lead to violent outgassing once the sun's warmth reaches critical depths, he explained, as layers of super volatile ices suddenly transition from solid to gas without passing through a liquid phase. But other researchers are less certain. Dr. Colin Snodgrass, an astronomer at the University of Edinburgh who specializes in cometary composition, emphasized that CO2-driven activity is inherently difficult to model. Carbon dioxide sublimates at temperatures far lower than water ice, and once it begins to vent, it can create feedback loops, escaping gas carves channels and cavities in the nucleus, exposing fresh ice, which vents more gas, which carves deeper. If 3I Atlas is rich in CO2, the outburst may be self-amplifying, driven by the comet's own internal structure rather than external heating. That would make predictions nearly impossible without knowing the exact layering and porosity of the nucleus, information that will not be available without a spacecraft flyby. No such mission is planned. Now about the data. The tail spans 0.7 degrees in the sky. At the comet's current distance from Earth, roughly 180 million kilometers, that angular size translates to a physical length of approximately 2.2 million kilometers. For perspective, that is more than 5 times the distance from the Earth to the Moon. The entire Moon could fit into one small segment of the tail, and there would be room for 4 more. The tail is not a plume. It is a river of ionized gas stretching across interplanetary space, and it has grown to that size in less than a week. The growth rate implies that 3I Atlas is expelling thousands of kilograms of gas every second, possibly tens of thousands, depending on the density and velocity of the outflow. To sustain that rate, the nucleus must be hemorrhaging mass at a pace that could reshape its surface within days. Read between the lines. If the comet is losing mass this quickly, it may not survive perihelion, the point of closest approach to the Sun, still weeks away. Comets have disintegrated before, torn apart by thermal stress or tidal forces. Comet Shoemaker-Levy 9 shattered into more than 20 fragments before colliding with Jupiter in 1994. Comet Ison broke apart during its 2013 perihelion passage, vaporized by solar heat. If 3I Atlas follows that path, it will not leave the solar system intact. Humanity will witness the death of an interstellar object in real time, a one-way journey that ends in dissolution rather than escape. The chemistry it carried from another star will be scattered across the inner solar system, mixed with solar wind and lost to analysis. The opportunity to study an alien world's frozen legacy will evaporate, literally, into the vacuum. Think about what that means. 3I Atlas may be the only sample of its parent system that ever reaches us. No telescope can resolve the star it came from. Trajectory analysis suggests the comet has been traveling through interstellar space for millions of years, possibly tens of millions, covering distances so vast that its origin point has likely moved far from where it was when the comet was first ejected. Stellar motion, galactic rotation, gravitational perturbations from passing stars, all of these have scrambled the comet's history. Even if researchers trace its orbit backward, accounting for every gravitational tug from every planet and every close encounter with the Sun, the trail will eventually grow too faint to follow. The comet came from somewhere, but that somewhere is now unknown and possibly unknowable. The only evidence is the ice itself, and the ice is evaporating. Here's where things get strange. The anti-tail, that faint projection extending opposite the main ion tail, is not just a geometric curiosity. It forms when large dust grains, too heavy to be pushed away by the solar wind, fall behind the comet in its orbit. Seen from the right angle, those particles align in a line, creating an illusion of a tail pointing toward the Sun instead of away from it. The presence of an anti-tail means 3I Atlas is shedding dust, not just gas, and the dust must be large enough and dense enough to resist radiation pressure. That implies the nucleus is fragmenting mechanically, cracking open under thermal stress, not merely sublimating smoothly. Dust production complicates the outgassing models further, because dust absorbs sunlight and re-radiates it as infrared heat, warming the nucleus more than bare ice would. The more dust the comet releases, the hotter it gets. The hotter it gets, the more gas it produces. The more gas it produces, the more dust is dragged along. Another feedback loop, spiraling upward. Competing explanations are now emerging from research groups worldwide. One hypothesis, favored by dynamicists, holds that 3I Atlas is an unusually pristine object, rich in super volatile ices like CO2 and CO, preserved because it formed in a system where giant planets never gravitationally stirred the outer disk. Such a disk would remain cold and quiescent, allowing ices to condense and remain undisturbed for billions of years. When the comet was eventually ejected, perhaps by a close encounter with a rogue planet or a passing star, it retained its primordial composition. Now, entering our solar system for the first time, it is experiencing heat it has never known, and the supervolatiles are responding violently. Another hypothesis, championed by astrochemists, suggests that the comet's interior contains amorphous ice, water ice that froze so quickly it never had time to form crystals. Amorphous ice is metastable, storing excess energy in its disordered molecular structure. When warmed, it transitions abruptly to crystalline ice, releasing that energy as heat. The phase change can be explosive on a molecular scale, cracking ice and venting gas in bursts. If 3I Atlas is rich in amorphous ice, the current outburst may be a crystallization wave propagating through the nucleus, triggered by the first touch of solar warmth. The wave would be self-sustaining, each layer's crystallization warming the next, until the entire comet has converted. The process would be rapid, violent, and impossible to stop. A third hypothesis, more speculative but not implausible, invokes exothermic chemistry. Certain frozen compounds, stable in isolation, react vigorously when mixed. If 3I Atlas contains segregated layers of reactive ices, say methane and oxygen, or ammonia and formaldehyde, then fractures caused by thermal expansion could bring those layers into contact for the first time. The resulting reactions would release heat, accelerating sublimation and creating localized hotspots. This mechanism has been proposed for some of Saturn's icy moons, where subsurface chemistry may drive cryovolcanism. Whether it operates in comets remains unproven, but the possibility cannot be dismissed without detailed compositional data. Each hypothesis has strengths, each has flaws. The pristine ice model explains the CO2 abundance, but struggles to account for the outburst's suddenness. The amorphous ice model predicts rapid episodic activity, but requires specific thermal histories that are difficult to verify. The exothermic chemistry model is elegant, but rests on assumptions about internal layering that no observation can confirm. The reality may involve all three mechanisms operating simultaneously, or none of them. The comet is a black box, and the only output is light. Stop and consider that. Comets are among the smallest objects in the solar system that can be studied in detail from Earth. Asteroids can be visited by spacecraft, their surfaces mapped and sampled. Planets and moons can be imaged at high resolution, their atmospheres analyzed. But comets, especially interstellar comets, pass through the inner solar system too quickly for mission planning. By the time a spacecraft could be designed, funded, built, and launched, the target has already departed, accelerating back toward interstellar space at tens of kilometers per second. The only way to study 3I Atlas is to watch it from afar, collecting photons and trying to reconstruct the physics from the light alone. It is detective work conducted across 180 million kilometers of empty space, using instruments that were never designed for this specific problem. Yet, that is precisely what astronomers are doing. Observatories around the world have begun coordinating their efforts, pooling data to build a more complete picture. The Virtual Telescope project in Italy, operated by Dr. Gianluca Massi, is tracking the comet nightly, weather permitting, using a remotely controlled telescope to capture long exposure images that reveal fine structure in the tail. Spectroscopic observations are being conducted at the European Southern Observatory in Chile, where large apertures and high-altitude sites allow detailed analysis of the comet's emitted light. Radio telescopes are searching for emissions from carbon monoxide and hydrogen cyanide, molecules that can betray the composition of the nucleus even when the comet is too faint for optical detection. Space-based instruments, including the Hubble Space Telescope and the James Webb Space Telescope, are being considered for follow-up observations, though scheduling conflicts and technical constraints may limit their availability. The urgency is palpable. 3I Atlas is moving quickly, and every day brings new changes. The tail's length is increasing, the brightness is fluctuating, the dust production is evolving. If astronomers wait too long, the comet will reach perihelion, where solar heating will peak, and the outburst will either climax or the nucleus will fragment. After perihelion, the comet will begin its outbound journey, moving away from the sun and cooling down. Activity will wane, the tail will shrink, Within months, 3I Atlas will fade from view, retreating into the darkness beyond Neptune's orbit. Within a few years, it will cross the heliopause, the boundary where the solar wind gives way to interstellar space. It will not return. There are no second chances. Think about what that means for planetary science. Interstellar objects are the only way to study the outcomes of planet formation in other star systems without traveling there. Exoplanets can be detected and characterized, their masses and orbits measured, their atmospheres tentatively probed. But the small bodies, the comets, asteroids, and planetesimals that carry the chemical fingerprints of disk chemistry are invisible at interstellar distances. Only when one happens to pass through our solar system does humanity get a chance to examine it directly. Oumuamua, the first interstellar object, arrived in 2017 and departed before anyone realized what it was. 2I Borisov, discovered in 2019, was recognized quickly enough for coordinated observations, but it was a relatively ordinary comet, chemically similar to solar system comets. 3I Atlas is different. The CO2 abundance, the rapid outgassing, the structured tail, every detail suggests a formation environment unlike the one that built our own cosmic neighborhood. If the abundance of CO2 is confirmed, it may indicate that 3I Atlas formed in a disk that was not only cold, but also carbon-rich. In the solar nebula, carbon was distributed unevenly, concentrated in volatile compounds at large distances, but locked in refractory minerals closer to the Sun. A system with higher metallicity, more heavy elements than the Sun, might produce disks where carbon dioxide ice is more common, especially if oxygen is abundant relative to hydrogen. Alternatively, 3I Atlas might have formed around a star with a different mass. Low-mass stars, the red dwarfs that outnumber Sun-like stars by a factor of 10 or more, have much smaller habitable zones and much colder outer disks. A comet from such a system would be expected to carry more CO2, more CO, and possibly more exotic ices like nitrogen or methane. The chemistry is a message written in molecules, and the message says, "This place was not like home." Read between the lines. The structured tail, with its fine striations and episodic brightness variations, implies that the outgassing is not uniform. The nucleus is not a smooth sphere melting evenly. It is an irregular body, possibly elongated or fragmented, with active regions where ice is exposed and inactive regions where a dust mantle has formed. As the comet rotates, comets typically spin with periods of hours to days, the active regions cycle into and out of sunlight, creating pulses of gas and dust. Those pulses propagate down the tail, carried by the solar wind, creating the observed structure. The striations are fossil records of the comet's rotation, frozen in ionized gas. If the rotation period can be measured, the periodicity of the striations should match. If it does not, something more complex is happening: multiple active regions, precession of the rotation axis, or subsurface venting that does not align with the Sun's direction. Observers are looking for those patterns now, comparing images taken hours or days apart, searching for repeating features. Preliminary analysis suggests a rotation period of approximately 8 to 12 hours, though the uncertainty is large. If that estimate is correct, the nucleus is spinning relatively quickly, perhaps the result of outgassing torques that have spun it up over time. Fast rotation can influence how a comet evolves. Centrifugal forces may cause the nucleus to elongate or even split, especially if it is a loosely bound aggregate rather than a solid monolith. Some comets are known to be contact binaries, two lobes touching along a narrow neck, the result of a low-speed collision in the early solar system. If 3I Atlas is a contact binary, the outburst may be concentrated in the neck region, where structural weakness allows gas to escape more easily. Alternatively, the comet could be a rubble pile, a gravitationally bound cluster of smaller fragments, held together only by their mutual attraction. Rubble piles are fragile, susceptible to tidal disruption and thermal fracturing. If 3I Atlas is a rubble pile, it may not survive perihelion intact. Now about the data on the anti-tail. Dust grains large enough to form an anti-tail typically range from tens of microns to millimeters in diameter, far larger than the submicron particles that populate the main dust tail. Such grains are difficult to lift from the nucleus. Escaping gas can drag small particles easily, but large grains require either high gas velocities or mechanical ejection, chunks of ice breaking off, carrying dust with them. The presence of large grains suggests that 3I Atlas is fragmenting, not just sublimating. Fractures are opening, pieces are breaking away. The comet is not melting like an ice cube in the sun. It is shattering. Fragmentation is not unusual for comets. Thermal stress, driven by temperature differences between day and night, can crack brittle ice. Comets are poor conductors of heat, so the surface heats quickly while the interior remains cold, creating enormous thermal gradients. Those gradients generate stress, and stress leads to fractures. Once a fracture opens, gas trapped below the surface can vent explosively, widening the crack and ejecting debris. The process can cascade, each fracture spawning new ones until the nucleus disintegrates entirely. Comet Linear did precisely this in 2000, breaking into dozens of fragments over the course of a few days. Comet Schwarzmann-Wachmann 3 has fragmented multiple times, shedding pieces with each perihelion passage. If 3I Atlas is following that trajectory, the next few weeks will be critical. The comet will either hold together or fall apart, and there is no way to predict which outcome is more likely. Here's where it gets interesting. If 3I Atlas does fragment, the pieces will spread out along the orbit, creating a debris stream. Earth may eventually pass through that stream, years or decades from now, triggering a meteor shower. The meteors would be interstellar in origin, the first such shower ever observed. Their spectra, captured during atmospheric entry, would reveal the composition of the fragments in exquisite detail: elements, isotopes, even organic compounds. It would be a form of sample return conducted not by spacecraft, but by gravity and chance. The science yield could be extraordinary, but it would also mean the comet itself is gone, destroyed by the very process that delivered its fragments to Earth. A bittersweet outcome. Knowledge purchased at the price of the object that carried it. Broader implications extend beyond planetary science. The discovery of 3 interstellar objects in less than a decade suggests that such objects are far more common than previously believed. Early estimates, based on Oumuamua alone, suggested that the Milky Way might contain trillions of interstellar comets and asteroids, debris ejected from planetary systems during their violent formative years. The detection of 2I Borisov and now 3I Atlas supports that hypothesis. If interstellar objects are common, they represent a vast, untapped archive of information about planet formation across the galaxy. Every star that builds planets ejects some fraction of its raw material into interstellar space. That material wanders the galaxy, occasionally passing through other star systems, carrying with it the chemical signatures of its birthplace. Earth is swimming in a sea of interstellar debris, most of it too small or too fast to detect. The few that are spotted, like 3I Atlas, are the tip of an enormous iceberg. Think about what that means for astrobiology. Comets are known to carry organic molecules, the carbon-based compounds that serve as the building blocks of life. Amino acids, nucleobases, sugars, all have been detected in cometary samples and meteorites. If interstellar comets are common, and if they carry organics, then the chemistry of life may be seeded across the galaxy, transported from star to star by ejected planetesimals. Panspermia, the hypothesis that life spreads between worlds on comets or meteorites, has long been speculative, dismissed by many as untestable. But the discovery of interstellar objects makes it testable. If 3I Atlas carries organic molecules, and if those molecules differ from the ones found in solar system comets, it would prove that organic chemistry is not unique to our stellar neighborhood. It would demonstrate that the ingredients of life are widespread, distributed by the same chaotic processes that build and destroy planetary systems. No organic molecules have been detected in 3I Atlas yet. The spectroscopic observations to date have focused on simple volatiles, CO2, CO, CN, but organics are harder to detect. They require high spectral resolution, large telescopes, and careful calibration. The James Webb Space Telescope, with its infrared spectrographs, is the best instrument for the job, capable of identifying complex molecules even in faint comets. If JWST observes 3I Atlas, it may detect polycyclic aromatic hydrocarbons, formaldehyde, methanol, or even amino acids, depending on the comet's composition and the sensitivity of the observations. Such a detection would be transformative, confirmation that the chemistry of life is not a solar system specialty, but a galactic commonplace. But JWST time is precious, oversubscribed by a factor of 5 or more. Proposals must be submitted months in advance, reviewed by committees, and ranked by scientific priority. 3I Atlas was not anticipated. No proposal exists. Securing observing time will require a director's discretionary allocation, a mechanism reserved for transient events or targets of exceptional interest. Such allocations are rare, granted only when the scientific payoff justifies disrupting the planned schedule. The case for 3I Atlas is strong, an interstellar comet, unexpectedly active, carrying chemistry from another star. But it is not guaranteed. The decision will be made in the coming days, and if the answer is no, the opportunity will be lost. The comet will not wait. Here's the problem. Even if JWST observes 3I Atlas, the data will not arrive immediately. Space telescopes operate on tight schedules, and data processing takes time. Raw observations must be calibrated, corrected for instrumental effects, and analyzed. Spectra must be extracted, wavelengths measured, features identified. For a moving target like a comet, the process is more complex because the comet's velocity shifts the spectral lines, requiring Doppler corrections. It may take weeks or months before results are published. By then, the comet will have passed perihelion, and its activity may have changed dramatically. The observations will capture a snapshot, a single moment in an evolving process, and that snapshot may or may not be representative of the comet's overall composition. It is the nature of transient science. The object does not wait for the analysis to catch up. What comes next depends on the comet itself. If 3I Atlas continues to brighten, it may become visible to small telescopes or even binoculars, accessible to amateur astronomers worldwide. Citizen science networks, which have proven invaluable for tracking comets, supernovae, and asteroid occultations, could contribute observations that professional astronomers cannot obtain alone. The sheer number of eyes on the sky, distributed across time zones and weather patterns, provides continuous coverage that no single observatory can match. Amateurs have discovered comets, tracked outbursts, and provided data that led to major scientific breakthroughs. Their role in studying 3I Atlas should not be underestimated. Professional observatories will continue their campaigns, coordinating observations across wavelengths. Optical telescopes will monitor the tail's structure and brightness. Infrared telescopes will measure thermal emission from dust. Radio telescopes will search for molecular lines. Ultraviolet observations, if available, will probe the comet's interaction with the solar wind. Each wavelength reveals different aspects of the comet's behavior, and only by combining them can a complete picture emerge. It is a mosaic, assembled one tile at a time, constrained by telescope availability, weather, and the relentless march of the comet's orbit. Perihelion is projected for mid-December, roughly 1 month from now. As the comet approaches, solar heating will intensify. The outgassing rate will increase, possibly doubling or tripling. The tail may grow longer still, stretching across multiple degrees of sky, a naked-eye spectacle if the brightness holds. Or the nucleus may disintegrate, fragmenting under thermal and mechanical stress, and the tail will fade as the fragments disperse. Both outcomes are possible. Neither can be ruled out. The uncertainty is part of the story, the tension that drives the investigation forward. After perihelion, 3I Atlas will recede, moving outward past Mars, past Jupiter, past the Kuiper Belt. The solar wind will weaken, the tail will shrink, activity will decline, then cease. The comet will return to the frozen silence it knew before entering the solar system, a dark speck drifting through the void. Ground-based telescopes will track it as long as they can, until it becomes too faint to detect, a magnitude 20 smudge lost among the stars. Space-based telescopes, with their superior sensitivity, may follow it longer, but even they will eventually lose the signal. The comet will vanish, not because it has been destroyed, but because it has simply moved too far away. Read between the lines. The fleeting nature of the observation window is not accidental. It is intrinsic to the physics. Interstellar objects enter the solar system at high velocities, typically 20 to 30 kilometers per second relative to the Sun. They are not gravitationally bound. They are passing through, briefly perturbed by the Sun's gravity, then ejected back into interstellar space. The trajectories are hyperbolic, not elliptical, and hyperbolic orbits do not close. The object arrives, swings around the Sun, and departs, never to return. For 3I Atlas, the entire observable period, from discovery to disappearance, will span less than a year. In cosmic terms, that is an eye blink, a moment so brief it barely registers. Yet in that eye blink, the comet is offering a glimpse into another world, a snapshot of chemistry and physics from a place humanity may never visit. Stop and consider that. The universe is vast, almost beyond comprehension. The Milky Way contains an estimated 200 billion stars, and each star is a potential host to planets, moons, comets, and asteroids. Most of those bodies will never be observed directly. They are too far away, too faint, orbiting stars too dim to resolve with even the most powerful telescopes. The study of exoplanets has revealed thousands of worlds, but those studies are limited to gross properties: mass, radius, orbital period, atmospheric composition if the geometry allows transits. The fine details, the mineralogy, the isotopic ratios, the organic chemistry, remain out of reach. Interstellar objects bypass that limitation. They bring the fine details here into the solar system, within range of terrestrial instruments. They are samples delivered without the need for interstellar travel, dropped into humanity's lap by the chaotic dynamics of planetary formation. That makes every interstellar object precious, irreplaceable. The data gathered from 3I Atlas will never be replicated. If the comet fragments, if the observations are incomplete, if key measurements are missed, the opportunity is gone forever. The comet cannot be revisited. There is no backup plan. The science must be done now, in real time, with the instruments available, or it will not be done at all. That urgency is both exhilarating and terrifying, a high-stakes race against time and physics. The broader context is shifting. A decade ago, interstellar objects were theoretical, discussed in conference presentations and review papers, but never observed. Today, they are a new class of solar system body, recognized, cataloged, and studied. Dedicated surveys are being planned to detect them more efficiently. The Vera C. Rubin Observatory, set to begin operation soon in Chile, will scan the entire visible sky every few nights, detecting faint, fast-moving objects that previous surveys would have missed. Estimates suggest that Rubin could detect one interstellar object per month once fully operational, transforming the field from a rarity-driven science to a population study. With dozens or hundreds of interstellar objects to analyze, patterns will emerge. Are they mostly comets or mostly asteroids? Do they cluster in certain compositions, or do they span a wide range? Are there objects with unusual properties, extremely dark surfaces, anomalous outgassing, spectroscopic signatures never seen before? Each discovery will refine the understanding of how planetary systems evolve and what happens to the debris they eject. But the Rubin Observatory is not operational yet, and 3I Atlas is here now. The current generation of instruments must suffice, and those instruments are being pushed to their limits. Long exposures strain telescope schedules. Spectroscopic observations require large apertures and stable conditions. Radio observations demand hours of integration time to detect faint molecular lines. Every data point is hard-won, extracted from photons that traveled 180 million kilometers through space to strike a detector. The logistics are formidable, the technical challenges immense, but the scientific motivation is undeniable. 3I Atlas is a messenger from another star, and the message is encoded in ice. Think about what that means for the future. If interstellar objects are common, and if they can be studied in detail, they offer a new way to explore the galaxy. Instead of building starships or launching interstellar probes, technologies that remain beyond current capabilities, humanity can wait for the galaxy to send samples here. It is a passive form of exploration, opportunistic rather than planned, but it is exploration nonetheless. Each interstellar object is a data point, a single star's contribution to the collective knowledge of planet formation. Over time, over decades or centuries, enough data points may accumulate to map the diversity of planetary systems across the Milky Way, revealing which chemistries are common, which are rare, and which are unique. It is a grand vision, ambitious and patient, and it begins with objects like 3I Atlas. The comet does not know it is being watched. It does not know it carries scientific significance. It is simply an ice-rich fragment, a relic of planet formation, following the laws of physics as it has for billions of years. It was ejected from its birth system by gravitational interactions, perhaps a near miss with a giant planet, perhaps a stellar encounter that destabilized the outer disk. It drifted through interstellar space, moving at a few tens of kilometers per second relative to the local standard of rest, crossing light years of emptiness. It encountered no stars, no planets, no heat. The temperature dropped to a few Kelvin above absolute zero, and the chemistry froze in place, preserved against decay by the sheer absence of energy. Then, by chance, its trajectory intersected the solar system. The sun's gravity bent its path, accelerating it inward. Solar radiation began to warm its surface. Ice began to sublimate. The comet woke from its billion-year sleep and began to die. Here's where things get strange. The time scale of the comet's journey dwarfs human history. If 3I Atlas has been traveling for 10 million years, it was ejected from its home system when Earth's climate was cooling into an ice age, when early hominins were just beginning to diverge from other apes. If it has been traveling for 100 million years, it left its star when dinosaurs walked the Earth, when the continents were configured differently, when the Milky Way's spiral arms occupied different positions. The comet is older than mountains, older than ocean basins, older than most of the species currently alive. It is a time capsule, but the time it encapsulates is not human time. It is geologic, cosmic, indifferent to the brief flicker of civilization. That indifference is humbling. The comet does not care whether humanity studies it or ignores it. It will continue its journey regardless, moving outward into the darkness, gradually cooling until it is indistinguishable from the interstellar medium. Eventually, in millions or billions of years, it may encounter another star. It may be captured into a new orbit, or gravitationally scattered, or vaporized by a close passage. Or it may drift forever, a frozen wanderer in an expanding universe, outlasting stars, outlasting galaxies, until the cosmos itself grows cold and dark. The comet's story does not end when it leaves the solar system. It only pauses, briefly, in the light. Now about the data that remains to be gathered. Isotopic ratios, if measurable, would provide the strongest constraints on the comet's origin. Different stars produce different isotopic abundances depending on their mass, age, and metallicity. The ratio of carbon-12 to carbon-13 or oxygen-16 to oxygen-18 in the comet's ices could point to a specific type of stellar environment. Deuterium to hydrogen ratios, already measured in some solar system comets, vary widely and are thought to reflect the temperature and dynamics of the protoplanetary disk. If 3I Atlas has a deuterium ratio significantly higher or lower than solar system comets, it would confirm that its formation conditions were different. Such measurements require high-resolution spectroscopy, ideally in the infrared or millimeter bands, where isotopic shifts are most pronounced. They are difficult, but not impossible, and several observatories are equipped to attempt them. The nucleus size, still uncertain, would help quantify the mass loss rate. Estimates based on brightness and activity suggest a diameter of a few kilometers, similar to typical short-period comets. But without direct imaging, the uncertainty is large. Radar observations could, in principle, constrain the size, but 3I Atlas is too far from Earth for most planetary radar systems. The Arecibo Observatory, which could have attempted such an observation, collapsed in 2020 and is no longer operational. The Goldstone radar in California may be able to detect the comet if it comes closer, but the geometry and timing are not favorable. Size estimates will likely rely on thermal modeling, fitting the observed brightness and dust production to models of surface temperature and albedo, a method prone to ambiguity. The rotation state, as mentioned, is partially constrained by the tail structure, but direct measurements would require photometric light curves, continuous monitoring of the comet's brightness over hours or days. As the nucleus rotates, different areas come into view, and if those areas have different reflectivities, the brightness will vary periodically. The amplitude of the variation reveals how elongated or irregular the nucleus is. The period reveals the rotation rate. Such observations are time-intensive, requiring dedicated telescope time and careful photometry, but they are within reach of both professional and amateur observers. If the rotation period is confirmed, it can be compared to theoretical predictions and used to infer the nucleus's shape and internal structure. The chemical inventory will grow as more spectra are obtained. CO2 has been detected. CO, cyanide, and hydroxyl radicals are likely but not yet confirmed. Water, the dominant volatile in most comets, is harder to detect because it does not ionize as readily as CO2, and its emission lines fall in spectral regions that are difficult to observe from the ground. Space-based ultraviolet spectrographs, such as those on the Hubble Space Telescope, are better suited for water detection. But again, telescope time must be secured. The full chemical profile, volatiles, refractories, organics, isotopes, will emerge only gradually, assembled from multiple observations across multiple wavelengths, synthesized into a coherent picture of what 3I Atlas is made of and where it came from. Here's the problem. Even with perfect data, the comet's origin star will remain unknown. Tracing the orbit backward is limited by uncertainties in the comet's velocity and position, compounded over time by gravitational perturbations and galactic dynamics. The further back the trajectory is extrapolated, the larger the uncertainties grow, until the probable origin region encompasses a volume of space containing millions of stars. Identifying a single star within that volume is statistically impossible without additional information. Radial velocity measurements of every candidate star, astrometric data to track their motions, chemical fingerprints to match the comet's composition. Such a campaign is beyond current capabilities, though future surveys like Gaia may narrow the possibilities. For now, the parent star is anonymous, a ghost in the data, known only by the chemistry it left behind. Read between the lines. The anonymity is not a failure of observation. It is an intrinsic limitation, a consequence of the comet's long journey and the galaxy's chaotic dynamics. Stars move, disks evolve. Material is exchanged between systems in stellar nurseries, where young stars are packed close together. A comet ejected from one system may have incorporated ices from another, mixed during close encounters in the birth cluster. The chemistry may not even be pure, but a blend, a composite fingerprint that points to multiple origins. Disentangling those origins may be impossible, the information lost to time and entropy. The comet's history is written in a language that is only partially readable, and some chapters are missing, erased by billions of years of erasure. Yet what remains is extraordinary. The CO2 abundance alone is a discovery, a clue that interstellar comets are not merely solar system analogs, but distinct objects with distinct chemistries. The rapid outgassing is another clue, suggesting that interstellar comets may be more volatile-rich, more fragile, more prone to spectacular outbursts than their local counterparts. The structured tail, the anti-tail, the fragmentation, all are pieces of the puzzle, fragments of understanding that, when assembled, may reveal not just the story of one comet, but the broader narrative of how planetary systems work, how they scatter their debris, how that debris travels the galaxy, and what it carries. The long-term meaning is hard to ignore. We are at the very beginning of detecting interstellar objects, but the trend is set. Better surveys, more discoveries, sharper data. Within a generation, scientists may compare dozens or hundreds of interstellar comets to our own, finally separating universal patterns from local quirks. And within a century, a spacecraft might chase one down, land on it, and study alien ices directly. Not science fiction, just ambitious engineering waiting for its moment. For now, 3I Atlas can only be studied from afar. It refuses to make things easy, brightening, flickering, shedding fragments. But that unpredictability is its lesson. Interstellar visitors are diverse and complicated. Each is a one-shot experiment in how planets and comets form around other stars. The big question isn't whether scientists will learn something, but how much. Will the data reveal its birthplace or only tease possibilities? Will we catch the key molecules before the nucleus breaks apart? How much depends on luck, weather, telescope time, the comet's own fragile structure? Science at this scale is powerful and precarious. One thing is already clear. 3I Atlas proves that the galaxy is constantly mixing its ingredients. Material from distant suns drifts between the stars, occasionally passing close enough for us to study. Every grain of dust in this comet is a relic from a different world, untouched, unaltered, a preserved memory of another star's beginning. It is a fossil from a foreign planetary system, carrying chemical fingerprints that don't match what we're used to. If its carbon dioxide abundance holds up, if its strange behavior is typical, then our solar system's comets may be the weird ones. Our assumptions could flip. Maybe interstellar comets are the norm, and our local residents are just the leftovers of a quieter history. The comet doesn't give answers, only questions. More objects like it must be found before patterns emerge. It will take years, decades, and patience. There are no shortcuts. Right now, 3I Atlas is still racing inward, heating, venting, slowly tearing itself apart under sunlight. We observe, we analyze. We hope it survives long enough to tell us more. Soon it will fade back into darkness, leaving only data and mysteries. And one lingering thought. How many others like it glide past unseen? How much of what we call solar system material was actually delivered by ancient visitors long before Earth formed? The boundary between local and alien becomes blurry. 3I Atlas is a brief chapter in a vast galactic story, but it arrived at exactly the right moment. Its message is being written now in jets of gas and shards of ice, a reminder that the universe still has surprises, drifting